light, all these things. And that was the state of the art for a long time until this guy, Tim Ball, worked with Joe Barry of the Carnegie Institution of Washington, and came up with this empirical model of stomatal conductance. This is the, believe it or not, this is the state of the art of our knowledge of stomatal conductance in response to the environment. The stomatal conductance is some constant times the humidity at the leaf surface times the net CO2 assimilation rate divided by the CO2 concentration at the leaf surface plus another constant. So here's the slope, here's the intercept. This, if you plot stomatal conductance as a function of HS, A over CS, you get a straight line. And what's more, you get a straight line with a slope of 9 for C3 plants and 4 for C4 plants. And you can vary these parameters to get your data points however you want. Light intensity, nitrogen supply, changing VPD, changing light. The data all coalesce to a single line. It's a really useful equation for predicting stomatal conductance. Why do we have to predict stomatal conductance? Well, if we're interested in yield, let's say we want to know something about water stress effect on yield. We can model the crop canopy and come up with the environmental conditions that are appropriate for that canopy. What's their effect on stomatal conductance? Which, after all, if we want to do, if we want to ultimately come up with net CO2 assimilation rate, total conductance for CO2 times, we'll use this simplified equation, right? Assume this is our photosynthesis model. There are far more elaborate photosynthesis models than this. But the point is, you need to know the stomatal conductance. You need to know something about the stomatal conductance to predict the CO2 exchange rate. And so, how do you know that? How do you know what to do? This equation is very useful. Right? No insight into what's going on mechanistically in this equation, but very useful equation. One question arises, right? Well, here. So this is called Ball-Berry model for stomatal conductance. Then this guy from Australia, Ray Looning, came along and said, well, he didn't like VPD, or he didn't like RH, so he put it in terms of vapor pressures and, you know, added another term. And it's just an elaboration of the same model. But my question to you then is, humidity at the leaf surface, CO2 concentration at the leaf surface. That means within the boundary layer. How do you know what those values are? How can you use an equation like this? How do you know what the humidity is within the leaf boundary layer? How do you know what the CO2 concentration is within the leaf boundary layer? In Looning's model, he's got saturation vapor pressure deficit at the leaf surface. Same idea. How do you know what that condition is in the boundary? Turns out you can just partition if you know the ambient CO2 concentration and the internal CO2 concentration, that difference, you partition it according to the ratio of the boundary layer conductance, the stomatal conductance, the same ratio, and that's what these equations show. So you can use that. That equation is useful for estimating stomatal conductance and potentially useful in a model of photosynthesis that is related to productivity and yield. It's a lot more complicated, of course, than this, because so far I'm still talking about a single leaf. But then ultimately we want to go to a whole canopy outside in the environment. and you got a bunch of leaves in the canopy. And those leaves have different environments around them. In particular, they're getting different amounts of light. And you know light really affects stomatical conductance and photosynthesis. So after I finish up with these effects, environmental effects on stomata at the single guard cell level, after that, probably on the 20th, or a week from today, maybe Thursday, is we'll scale up single leaf to whole canopy conductances and see how to do that. How we these models have been used. This is just an example of a paper that modeling the response of canopies to model conductance to humidity. Right. So here, canopy conductance, humidity. They're very useful. That's all. So on Tuesday, I'll start here with stomatic, still on this idea of water stress, stomatal response, and the leaf-water relations. As water stress increases, the leaf-water potential typically decreases. What's the interaction between those factors? That's where I'll. So have a good weekend. Stay warm.